All right, welcome. So we are going to talk today about section 6.3. Section 6.3 is binomial and geometric random variables. Today we're just going to talk about binomial random variables. So quick pop quiz, ready? Circle the correct answer. It's a multiple choice quiz. Here you go. Circle your correct answer. 10 questions. So you can pause the video here and find the best answer choice. You're probably thinking kind of silly, right? It is kind of silly. But there's a reason we're doing this. So pause the video, circle your best answer choice. All right. Now that you've taken your little pop quiz, let's check your answers. Let's see how you did. How many answers did you get correct? So pause the video one more time, check your answers. So essentially you were kind of guessing on this quiz, right? You were guessing. There were 4 answer choices. So theoretically, you had about a 25% chance, 1 out of 4 chance of getting each question correct, right? So this is essentially what we call a binomial situation. You either got the answer correct or you got the answer incorrect, and you had a 25% chance of getting the correct answer on each question. There were 10 questions on the quiz. Everyone who just took this little pop quiz answered 10 questions. This is essentially what we call a binomial situation or a binomial random variable. And we're interested in how many answers we got correct. So a binomial setting arises when we perform n independent trials of the same chance process. So in other words, the pop quiz that you just took, your responses, or whether you got each question right or wrong, was independent from one another. So if you got the first question wrong, that didn't necessarily affect, if you got the second question right or wrong. And then we count the number of times that a particular outcome, and we're going to call that a success, occurs. In other words, we counted how many questions you got quote unquote correct on your multiple choice question or your multiple choice test. So there are 4 conditions for a binomial setting. Binary, in other words, there has to be 2 possible outcomes. And we call the 2 possible outcomes a success or a failure, and sometimes failure, that can be a little bit misleading. For example, on your multiple choice question or your multiple choice quiz, if you got the question right, we are going to call that a success. If you got it wrong, we'll call that a failure. And that kind of makes sense. It's a failure if you got it wrong. But sometimes we might even be looking for something like the gender of a baby. So when you have a newborn baby, is the baby a girl or a boy? If we're interested in the number of girls that we have, we're going to call having a girl a success, having a boy a failure. Now that does not mean that it's a failure to have a boy in the typical sense. It just means that that's not necessarily what we're looking for. So the second condition is that we have independence. The trials must be independent. Knowing the outcome of one trial must not tell us anything about the outcome of any other trial. And in the multiple choice question, the multiple choice quiz you took, there were 10 trials. So again, if I got the first one correct, that doesn't really tell me anything about whether or not I'm going to get the second one or third one or fifth one, etc. correct. Number. So the number of trials, there were 10 multiple choice questions, is fixed in advance. So everyone who just took that quiz took a 10 question quiz. If I gave some people a 10 question quiz and some people a 4 question quiz, then we wouldn't have the same number. And then the same probability, we call that probability of success P. So for each question on the multiple choice quiz, there were 4 choices. There were 4 answer choices. If I gave a multiple choice quiz where numbers 1, 2, and 3 had 3 answer choices, only like A, B, and C, but then the rest of them had 4 answer choices, A, B, C, D, then I wouldn't have the same probability of success. So then that wouldn't be binomial. So you have to kind of know these these four conditions. You have to have these memorized. You're going to be asked to check, is this a binomial situation? And sometimes it won't even specifically say, is it binomial? It'll just say something like, what type of a situation is this? And you'll have to check. So just like a quick way to kind of try and remember, check bins. So whenever you have a binomial situation, these four conditions, we can think of binary, independence, number, and S, B-I-N-S, bins. So if we have a discrete random variable x, where x is the number of successes in n trials, if that's a binomial random variable, then we can use this notation, and we can say that x follows the random variable, or x is a random variable that follows a binomial distribution with parameters n and p. So remember, n is the fixed number and p is the probability of success, the fixed probability of success. And a lot of times, to make these like numerical outcomes, you know, like we said in the in that multiple choice quiz, you either got the question right or you got the question wrong. But a lot of times, to make those like numerical outcomes, we can label a success as a 1 and a failure as a 0. So if you got the question correct, you would count that as like one question correct. If you got the question wrong, that would be like no questions correct, if that makes sense. So let's jump into kind of some examples. Determine whether the given scenario describes a binomial setting and justify your answer. So take a minute, read this. So genetics says that the genes children receive from their parents are independent from one child to another. Each child of a particular set of parents has a probability of 0.25 of having type O blood. Suppose these parents have 5 children. Count the number of children with type O blood. So is it binomial? So we got to check bins, right? B-I-N-S, bins. So binary, meaning do we only have 2 possible outcomes? So a success would be having a type O blood child. A failure would be having a child without type O blood. So again, you know, just because you don't have type O blood, that's not necessarily a bad thing, but that's not what we're looking for in this situation, so we call that the failure. So independence. Knowing one child's blood type does not really tell us anything about the next child because they inherit genes independently from their parents. So we have independence here. Number. They're telling us that these parents are having 5 children. So that's like a fixed number. And then probability of success. Remember, we labeled a success as having type O blood. So each kid has a 25% chance of having type O blood. So because these 4 conditions are met, we can say that this is a binomial situation, okay? And we're going to actually revisit this problem a couple times throughout our video today. Let's look at this one. So shuffle a standard deck of 52 playing cards, turn over the first 10 cards one at a time. Record the number of aces that you observe. Is it binomial? So in this case, we're going to, again, check bins, right? A success is if we get an ace. A failure is if we don't get an ace, right? So we have the binary component, but do we have independence? So because you're turning over cards one at a time and you're essentially like not replacing the cards back in the deck, we don't have independence. So in other words, if I read this, if the first card you turn over is an ace, then the next card is less likely to be an ace. So it changes the probability. We don't have that fixed probability, therefore we don't have independence. So this is not binomial. Okay, here's another one. Shuffle a deck of cards, turn over the top card, put the card back in the deck, shuffle again. And repeat this process until you get an ace. Count the number of cards you had to turn over. Is it binomial? So it's similar to the one we just looked at, but it's a little bit different, right? So we still have the success versus failure. Now we have independence because we are replacing the card, right? But Here's the problem. We don't have this fixed number of trials. We're repeating the process until we get an ace. So I don't know, how many trials I'm going to do. If I change this and I said, repeat this process 10 times, then this would be binomial. But in this case, this is, again, not binomial. So again, just some more examples and non-examples of binomial situations. So kind of read through this list. If I flip a coin 3 times and I count the number of heads, I'm just going to skip down. Number 4, when I roll a 6-sided die, we're interested in how often we'll roll a 4 or a 6 out of 10 total rolls. So in this case, my successes would be rolling a 4 and a 6, 4 or a 6, sorry. My failure would be rolling a 1, 2, 3, or a 5. So even though it's 2 possible outcomes, I can still say the probability of success is 2 out of 6, right? I still have independence, so even number 4, that is still binomial. Jumping back to number 3, the number of men who are 6 foot or taller in an SRS of 10 men. And so because it's an SRS, we're assuming that this is out of like a large population. So we should have independence. That should be binomial. Some non-examples of binomial situation, we kind of just talked about something similar to number 1. If I don't have replacement, if I'm picking cards out of a deck. And then option 2, or example number 2, any situation where there are more than 2 possible outcomes. All right. So we're going to go back, like I said before, and revisit this blood type kind of scenario. So we already established that this was binomial. We already talked about bins, right? Those 4 conditions. So now I'm going to let X, I'm going to define my random variable. So I'm defining my random variable. And remember, just a quick reminder for early in the chapter, a random variable, it's a random process and it has a numerical outcome. So X is the number of children, right? It's a numerical outcome. So it's the number of children with type O blood from that family of 5. And so we said that X is binomial. So now we have a binomial random variable. So the probability distribution of X is called a binomial distribution. So the count of successes, X, in a binomial setting is a binomial random variable. So the possible values of X are 0, 1, 2, all the way up through N. In this case, we said that this family's having 5 kids. So the possible values of X are 0, 1, 2, 3, 4, and 5. So the binomial distribution is specified by 2 numbers, the number of trials, N, and the probability of success, P. And remember, so we could say in this case, our random variable that we defined here follows a binomial distribution, and because they have 5 kids in the family, N is 5, and the probability of success, they told us that the probability of having each kid with type O blood is 25%. All right, so that tells us that X follows a binomial distribution with N equals 5 and P equals 0.25. So again, same problem. What if we asked you this question? So what's the probability that exactly one of the 5 children has type O blood? So same question, we're having 5 kids. Each kid has a 25% chance of having type O blood. What's the probability that exactly one of those 5 kids has type O blood? So I'm just going to jot down some information, some stuff that we know, right? So let me define the events: O being a child with type O blood, N being a child that doesn't have type O blood, so not with type O blood, N for not. So the probability of O is 0.25, the probability of N is 0.75, right? So I want 1 kid with type O blood and 1 kid not with type O blood. Because these things are independent, I can just multiply these probabilities together. So I want the probability of 1 type O kid and 4 not typoed kids, right? So 0.25 times 0.75, 0.75, 0.75, 0.75, or 0.75 to the fourth, right? So that's one kid not, one kid with typo, 4 kids not. So that gives me 0.079. But here's the but. Ready? There are many ways to have 5 kids with various blood types, or in other words, many different combinations. So that's an important word we're going to kind of revisit. So here's all my possible outcomes. This took me a while to list these all out, right? It's kind of a pain in the neck. I could have, when I have, like, think of if you're the parents and you're having these kids, you could have your first kid with typo blood, your second kid with typo blood, third kid with typo blood, fourth, and then fifth with typo blood. Or you can have this order of kids. So all of these, think of these as like specific orders, you know? So like this one, for example, right here. My first kid had typo blood, my second and my third did not. My fourth one did have typo blood, and then my fifth one did not, right? So that's essentially what that kind of means, okay? So because there's all these different ways that like these orders in which the kids could kind of come out, right? I need to figure out how many of these combinations give me 1 kid with type O blood and 4 kids with not type O blood. And so if I go through my list, you can see I circled those combinations. I have 1, 2, 3, 4, 5 different ways of having this combination of 1 type O blood kid and 4 not. So I have to take this probability that I already came up with, this 0.079, and I have to multiply it by 5. So really, my answer to this question, what's the probability that exactly one of the 5 children has type O blood? That probability is 0.396. So just to kind of like clean things up, make it look a little bit nicer, this is the same thing that we just looked at. But let's talk about notation as well. So remember, we defined x before. X is our random variable. X was the number of kids in the family with type O blood, right? So we found the probability that x is equal to 1. In other words, that we had 1 kid with type O blood. So that probability was, in words, the probability that exactly 1 child has type O blood. And what we did was we multiplied 5, and 5 was the number of ways to get 1 child out of 5 with type O blood. And then we multiplied that by the probability of success, and we raised it to the first power because there was 1 child with type O blood. And then the probability of failure of 0.75 raised to essentially the number of failures, the number of kids that didn't have type O blood. So that's essentially the formula that we kind of used, that we kind of came up with. And in words here, take a minute to read this, we're going to kind of generalize. The probability that x is equal to k is equal to the number of ways to get k successes out of those n trials times the probability of success raised to the number of successes. Remember, k is the number of successes, times the probability of failure raised to the number of failures. Well, the number of failures is the total number of trials, which is n, minus the number of successes, which is k. So let's focus more on, let me go back a second, on this, the number of ways to get k successes in n trials. So we're going to talk about something called our binomial coefficient, and you might have seen this before. This is, in other words, called combinations. If you've heard of like combinations and permutations, right? So this is a combination. So notation Sometimes you'll see this as like NCK, where um, C is like a capital letter C. You can also see it written as like the N and the K. That's not a fraction, okay? But this notation here, or this notation here, means we want a combination. N choose K. That's how we read that. N choose K. So that's defined to be N factorial. It's exciting. N factorial, we call that exclamation point. In math, we call that a factorial. So N factorial over K factorial times N minus K factorial. So N factorial is N times N minus 1 times N minus 2, et cetera, et cetera. So for example, like 5 factorial is 5 times N minus 1, so 4 times N minus 2, so 3 times 2 times 1. That's what 5 factorial is, okay? 0 factorial is a little tricky. We define 0 factorial to be equal to 1. But so, just again, another reminder that binomial coefficient, we read this as N choose K. It has nothing to do with N divided by K, right? N choose K is defined to be this up here. It's not a fraction. But if we use this binomial coefficient or these combinations, that's going to give us kind of the number out in front here. Remember the number of ways that we can have one success in our 5-kid family. All right, so here's our formula. We're going to take that binomial coefficient, and we're going to use that in our formula for binomial probabilities. So suppose that X is a binomial random variable with N number of trials and P probability of success. So the probability of getting exactly K successes in N trials is this. We're going to use this as the formula. It might look crazy, but think about it. We kind of like derived this formula when we looked at that type O blood with the family, right? So N choose K tells us how many different ways can we order, or how many different ways can I have 5 kids and have 5 total kids, and one of those 5 has type O blood. Probability of success is P. The number of successes is K. Probability of failure is 1 minus P. Number of failures is N minus K. So that's our formula there. And again, we define N choose K to be this. That's our combinations. So just as a quick reminder, anytime you use this formula, you must have already stated that this is a binomial situation. So what that means is maybe in the problem they told you this is a binomial situation. To be honest, that doesn't happen very often. More likely, you say, oh, here's this problem I got. This is binomial because of these 4 things: binary, independence, fixed number N, and same probability P. And because it's binomial, now I can use this formula, and you'll kind of see what I mean. So, same example, but now we want to find the probability that X is equal to 3. So in other words, we want the probability that the same family is going to have 3 kids with the type O blood. So before I do anything, I first have to state that X is a binomial random variable. We've already done that a couple times now, okay? But if I didn't already do it, I have to do it. So check, I already did that. Now, using my formula, the probability that X is equal to 3 is going to be equal to 5 choose 3. Remember, that tells us I have 5 total kids, but I have, out of those 5, I have 3 with type O blood. But how many different combinations with 3 kids can I come up with, right? So 5 choose 3 times probability of success is P. So this is P to the number of successes. I have 3 successes. And then the probability of failure, 1 minus P. And to the N minus K, so the number of failures. So here's my formula, right? Now, how can we do this on the calculator? Let me get my calculator over here real fast. So you can use your calculator to come up with combinations. It's under the math PRB or PROB, so math probability menu. All right. And then you can see I have this NCR. It's my third option there. That's a combination. So in this case, we have 5 kids in the family total, and we want 3 of them to have type O blood, or in other words, 3 successes. So 5 choose 3. If I hit enter, it gives me 10. In other words, remember I had that big long list of like all the different ways I could have like OOOOP, whatever, or OOOON, whatever. So there's 10 of those different combinations that had 3 kids with type O blood. All right, so that's using the calculator. Here you can see that here. So if I calculate 10 times 0.25 to the third times 0.75 to the second, this is what I get. In other words, let me interpret it. There's about an 8.8% chance or probability that exactly 3 out of the 5 children have type O blood. So, next question. Suppose the parents have 5 children. Should the parents be surprised if more than 3 of their children have type O blood? So should they be surprised? So hopefully that like triggers off something in your head. We're talking about like statistical significance, right? Is this likely? So let's figure it out. Is it likely? So we're interested, is it likely that more than 3 of their kids have type O blood? So again, we've already established that this is a binomial distribution. But if I asked you this question cold on like a quiz or something, you would have to go through bins to tell me this is binomial before you use these formulas. So anyway, what we're going to do is we're going to find the probability that x is greater than 3, because it says more than 3 of their children have type O blood, right? So the probability that x is greater than 3, that's the probability that x is equal to 4 plus the probability that x is equal to 5. So now I have kind of like 2 of these binomial formulas that I'm adding together. So, oh, and this is, sorry guys, this is a little typo. This should be 5 choose 5. I have 5 successes and I have no failures, okay? So this is the probability that x equals 4. This is the probability that x is equal to 5. Type those into your calculator, add them together, and we see that there's about a 1.563 chance of having more than 3 kids with type O blood. So down at the bottom, that's a pretty small chance. That's pretty unlikely, right? So because there's only about a 1.5% chance of having more than 3 children with type O blood, the parents should be surprised if that actually does happen, right? There's only a 1.5% chance of it happening. So it's pretty unlikely that it's gonna happen. So if you think back to when we talked about like normal distributions, we use the calculator, we use like normal CDF and normal PDF. Hopefully you remember that, to calculate areas under the normal distribution, under the normal curve. Well, your calculator can do the same thing with binomial distributions. So just as a quick reminder, a PDF points to a specific value in a random variable, and a CDF accumulates area. So to use the calculator, a binomial PDF calculates the probability that x is equal to a certain number. Okay, so if we want to find the probability that x, the random variable, binomial random variable x is equal to 3, we can use binom PDF, and I'll show you in just a second where you find this. So in this situation, n is 5, because we're having 5 total kids. Probability of success is 0.25, and we want 3 successes. On the other hand, the second question that we looked at was, what's the probability that you have more than 3 kids with type O blood, right? So that would be a CDF, because you want to like accumulate area. So we want the probability that X is greater than 3. Well, a binomial and a normal CDF only give you the area below a certain point. So if you use the binomial CDF function on the calculator, if you use, and again, n equals 5, probability of success, p is 0.25, and k equals 3, this function, this 0.984375, that gives you the area less than or equal to 3. So that gives you the probability that you have 3 or less kids with type O blood. So to find the probability that X is greater than 3, we have to take 1 minus that. And just be careful, because this is a discrete random variable, there is a difference between X is less than or equal to 3 and X is less than 3, right? Because we can calculate the probability that X is equal to 3. So that's how I would use the calculator in that way. Let me real fast bring my calculator back over for one quick second and show you on here where those menu options are. So if I go to, see, remember distribution is on top of var, so I have to hit second. I'm on the home screen, so I start on the home screen, I hit second, vars or distribution, and here was my normal PDF, normal CDF, right? Just as a quick reminder from like chapter 2, but remember, we're not dealing with normal distributions, we're dealing with binomial distribution, so I have to scroll way down on my calculator, but here I have binom PDF, binom CDF. So binomial PDF, trials was 5, probability of success was 0.25, and we wanted 3 kids with type O blood, right? So my X is 3. I paste that in. Oops. What did I? Oh, it gave me too many decimal points, sorry. There you go. So that was our 0.0878. On the other hand, the second problem that we did, binomial CDF, so I have 5 total kids, the probability of success is 0.25, right? And if I type in X is 3 and paste that, this gives me the probability that X is less than or equal to 3. So remember, if we want the probability that X is greater than 3, we do the 1 minus second answer. So that's using the calculator to calculate those binomial probabilities, okay? All right, so just to like kind of recap, anytime you have to find a binomial probability, you're going to state the distribution, so state that it's binomial, and the values of interest. You have to specifically say that this is binomial because of these 4 things, in other words, bins, and give the number of trials n, this fixed probability of success p, and you have to clearly identify the variable, meaning, like we said, that X is the number of kids that have type O blood in this family. And then step 2, perform your calculations. Always, we have to show our work, right? Now this probability formula is on your formula sheet, so you can use the formula, or you can use the calculator inputs like binom PDF or binom CDF, but you have to be sure that you label each of the inputs, okay? And you'll see in just a second what I mean, but then answer the question. Make sure you interpret or answer the question that was being asked. So look, let's look at another example. A local fast food restaurant is running a draw free, get it free lunch promo. After each customer orders, a touchscreen display shows the message, press here to win a free lunch. So a computer program then simulates 1 card being drawn from a standard deck. If the chosen card is a 3, the customer's order is free. Otherwise, the customer must pay the bill. Okay, so on the first day of the promotion, you have 250 customers that place lunch orders. So find the probability that fewer than 10 of them win a free lunch. Now remember, obviously, we're in the middle of talking about binomial probabilities. The title slide says calculating binomial probabilities, but you still, in the problem, I never told you that this was binomial. So we still need to check, is it binomial? So we're checking bins, okay? So that's the first thing we're doing. So you can see down here, binary. The card is either a 3 or it's not a 3. So a success would be getting a 3 that they win, not a success would be not getting a 3. Independence, we're going to assume that each card draw is independent. In other words, we're assuming that the deck is like reset after each trial. And I put reset in quotes because it's computer, it's a computer program. But N, we have 250 customers. That's our fixed number. And same probability, the probability of success, in other words, the probability of winning, or in other words, getting a 3, there's 4 3s out of my deck of 52 cards. So this tells me, because these 4 conditions are met, that Y is binomial with N equals 250 and P equals 452. So first of all, I said that this is all binomial, and I also defined the random variable. So I used Y to represent the number of customers on this first day who win a free lunch, right? So this is like, my question was find the probability, right? I'm not doing anything with probability yet. This is all kind of like the setup, the pre-work. This is required. Let me be clear. Let me say it again. This is all required. If you just have numbers, you're going to get less than half credit, okay? Because this is a part of the problem. Okay, so now let's actually find that probability. So the probability that fewer than 10 of them win a free lunch. So we want the probability that Y is less than 10, which is equal to the probability that Y is less than or equal to, that should be a 9 there, sorry guys. Because again, I'm going to use the calculator, and my calculator can't give me any less thans. It only gives me less than or equal to's. So the probability that Y is less than 10 is equal to the probability that Y is less than or equal to 9. So using the calculator, and I'm allowed to write this down if I know I'm CDF, but notice that I clearly labeled the number of trials is 250, the probability of success is 4 out of 52, and that the number of successes, or the X value, is 9. So in other words, there's a 0.6% chance of fewer than 10 customers winning a free lunch. So same situation, but in this case, only 9 customers actually want a free lunch. Does this result give convincing evidence that the computer program is flawed? So hopefully this should like set off bells. Ding, 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 ding. We're talking about statistical significance. So because there's only a 0.006% probability or chance that fewer than 10 customers would win a free lunch. Remember, we said typically like 5%. This is less than 1%, right? So 5% is like our kind of like cutoff. So because this is so rare, it would only occur so rarely. If this is what actually happens, then we have convincing evidence that the computer program is flawed. And that essentially this is saying the computer program is not really simulating one card being drawn from a standard deck. It's like rigged, right? Okay, so that was binomial probabilities. We were calculating binomial probabilities. Now we're going to look at the distribution as a whole. So the binomial distribution as a whole, okay? And we are going to describe that distribution. right? We're going all the way back to like chapter 1 when we describe distributions. So when we describe distributions, we're talking about SOCs, right? Shape, center, outliers, spread, or variability. So same question with this number of kids in this typo blood family, right? So this table shows all the possible values and their corresponding probabilities for X is the number of children with typo blood from that family. So again, this is a binomial random variable with n equals 5, p equals 0.25. We've proved a couple times now that this is binomial. But so we already calculated some of these probabilities. We calculated this value by hand. That was the first thing we did. We found the probability that X equals 3 on the calculator, right? So you can double check using your calculator. You could build this probability distribution table using the calculator, but this is what the table is going to look like. So in other words, you could go to your calculator and you could type in second distribution, we scroll all the way down, binomial PDF, 5 kids in the family, probability of success is 0.25. What's the probability, let's say that you have no kids with type O blood? So 0.237, right? So that's how we get that 0.237 number. So again, we're just going to use the calculator, and you can pause the video and kind of double check and fill in all of these probabilities. So that's our probability distribution table. Now, if I were to take all of these values and make a histogram, X is the number of children with type O blood. So again, we're having 5 kids. So how many of them have type O blood? Either 0, 1, 2, 3, 4, or 5. And then what's the probability of each of these things happening? That's what goes on our y-axis, right? So literally you can see the probability from my table that we just found on the calculator. The probability of having no kids with type O blood was about 23, 24%. Boom, this purple bar goes up to about 24%, right? So we can kind of look at this distribution. This is the distribution for this random variable X. And the shape, we're going to describe the shape, the center, and the variability of this distribution. We can pretty clearly see that this is skewed right. So, like I said, we are going to describe all of these binomial distributions, but I want to take a minute and we're going to look at shape first. So the shape of a binomial distribution is going to actually depend on n and p. So let's look at the example that we've been looking at. So we have 5 kids in the family. The probability of success is 0.25, right? So this is exactly the same histogram we just looked at, right? We've seen that number a couple times now. The probability of having 0 kids in the family with type O blood was about 24%. We can see it again here, right? So this should look similar. And we calculated what's the probability of, I can like highlight this here. What's the probability of having 0 kids? What's the probability of having more than 0 kids with type O blood, or less than 0 kids with type O blood? I'm going to just kind of leave that blank for a second. But if I mess around with n and p a little bit, so I want to kind of show you what happened. So in this case, there was a 25% chance of success, right? So a 25% chance of success. This is what the distribution looks like. Well, what if I now make it a 75% chance of success? So this is now, I'm still having 5 kids in the family, and there's a 75% chance that each kid has type O blood. Well, if there's a 75% chance, doesn't it make sense that I would have probably more kids with type O blood in general? Watch what happens. This whole distribution kind of shifts. And now it's the same exact probabilities, except for kind of like backwards. The probability of having 0 kids before was 24%. Now the probability of having 5 kids with type O blood is about 24%, right? Because it's so much more likely that I have, that each individual kid has type O blood. So overall, in general, I would expect to have more kids in my family with type O blood, right? So now we went from being right skewed to now left skewed. Now, what do you think is going to happen if I change the probability of success to 0.5? So now if there's a 50% chance of each kid having type O blood, so there's a 50% chance of each kid having type O blood, this is what my distribution looks like. It looks pretty symmetric, right? Think about it. If there's a 50% chance of each kid having type O blood, about half of my kids should have type O blood and about half of them shouldn't, right? So most of the time, you're going to have about 2 or 3. I can't have 2.5 kids with type O blood. So I'm going to have either 2 or 3 kids with the type O blood, right? So you're going to see that the shape of a binomial distribution is going to change based upon N and P. So we were playing around, we were changing P, the probability of success. Now let me change N. Let me make N like 100. So now let's say I'm having 100 kids. Woo! 100 kids, and I want to find out how many of them have type O blood. If there's a 50% chance that each kid has type O blood, you can see the shape is symmetric, right? And it's centered around 50. But let me change this back to 0.25. Whoops. 0.25. Look, this is weird. It's still symmetric. But now you might have noticed that the shape is symmetric, but it's now centered around 25 kids. And you can see down here my mean is 25. Let me make N a little bit smaller. Let me make N something like, now instead of going crazy and having 100 kids, let me have like 10 kids. Well, when N is 10 and P is 0.25, I'm kind of going back to being right skewed a little bit, but it's not quite as right skewed as it was when N was just 5, right? So hopefully you can kind of see that. Let me change this to N equals 8. And then let me change it to 10 again. And then let me change it to 20. You can kind of see that the shape of my distribution is changing dependent upon both of these things. If I change P to like 0.1, N is 20, N is 5. So I can get like a right skewed distribution. Let me change this to 0.9. I can get a left skewed distribution. I can get a symmetric distribution. And hopefully it makes sense to you that as P gets bigger and bigger, closer to 1, the distribution is going to get more and more left skewed because we would expect more and more successes. As P gets smaller, closer to 0, the distribution is going to get closer and closer to a right skew because I'm going to have less successes. And when P is close to 0.5, my successes would be like half and half in the middle. So it would be kind of symmetric, right? It's kind of what we would expect when we think about it. So that's a little bit about shape. And here's just a couple more examples. Here's an example of a binomial distribution with N equals 5 and P 0.51. Again, because the P is close to 0.5, it's pretty symmetric. That's what we would expect. But when we have more successes than failures, so if P is 0.8, it's kind of more skewed left. Again, kind of what we just talked about. That's what we would expect. So it's going to seem like I'm switching gears for just a second, but you'll see how this kind of all comes together. We're going to talk about something called a Bernoulli random variable. All right, so if a random variable is binomial, B means that capital B is binomial, with N and P, then the probability distribution of a single observation, or like a single trial. So in other words, let me go way back to the multiple choice quiz that you took in the beginning of this. If I only gave you one multiple choice question, you either get that one question right or you get your one question wrong. So in other words, when N is 1. So it's kind of like binomial, but N is just 1. We call that a Bernoulli distribution. So the sum of many Bernoulli observations is called the binomial, right? Okay, so let's just focus on when I just have one trial. If I just have one trial, in other words, a Bernoulli random variable, on that one multiple choice question, I either get it right or I get it wrong. I either have a failure or a success. So the probability of success, just like always, we call P. The probability of failure, just like always, let's call that 1 minus P. But let's now define that to be equal to Q. So the probability of failure, let's call that Q for a minute. So I'm going to apply my formulas for mean and standard deviation of random variables from earlier in chapter 6. So the mean of my Bernoulli, remember we're just doing one trial. To find the mean, I multiply each outcome times the probability of the outcome. So 0 times Q plus 1 times P, right? 0 times Q, that's 0. So the mean, or the expected value, is just 1 times P, or in other words, P, right? Now let's plug in. I want to find standard deviation, so I'm going to plug in to find the variance first. So remember, to find the variance, I take the individual outcomes, the x values, and subtract the mean from it, so 0 minus P, but then I square it to make them all positive. And then remember, I weigh that by multiplying by the probability of success, or I'm sorry, the probability of each outcome. I'm sorry, I didn't mean to say success. So times Q. And then I add that to 1 from here minus the mean is P squared, times the probability of that outcome. So that's this P here, right? So that's my formula for variance. So let me do some simplifying. 0 minus P is just negative P, but then when I square it, that's going to be a positive P squared, right? So this is like P squared times Q plus, and then 1 minus P. This 1 minus P, remember, I defined 1 minus P to be equal to Q up here. See that? So I'm going to rewrite that as Q squared times P. Now let's think back to your algebra. Hopefully you can see I have some Q's and I have some P's. Let me factor out a common factor. So they both have a P and they both have a Q in common, right? So I'm going to factor out a PQ, and I'm left with just P, because P squared divided by P, plus Q squared divided by Q is just Q. So when I factor out my greatest common factor, now look, I have P plus Q. Well, P is the probability of success, Q is the probability of failure. When I add them together, I should get that equal to 1. So this whole thing here is just 1. So in other words, sigma squared, or the variance, is just P times Q times 1, or in other words, just P times Q. So my variance is PQ. Remember, we really care about our standard deviation. So my standard deviation of x is the square root of PQ. All right? So there's my mean, here's my standard deviation. Remember, this is of a Bernoulli random variable. So this is like one multiple choice question. So now let me kind of take this idea of like my Bernoulli random variable and go back into the binomial situation. So remember, a binomial is many Bernoulli observations. Well, how many? It's 4. Or I'm sorry, 5 in the 5-kid family, or n, however many n is. So in other words, y is the number of successes in n trials. So think of all these x1, x2, all the way up through xn. These are all these little Bernoulli random variables. So if I'm having like the 5-kid family, I have 5 Bernoulli random variables. And your 10 multiple choice quiz question in the beginning, you have 10 Bernoulli random variables. You add them all together, okay? When we add these all together, that's the binomial situation. So let's apply our rules for random variables from earlier in the chapter. The mean that I just came up with, the mean of my Bernoulli random variable, and I'll write like Bernoulli, B-E-R for Bernoulli, was just equal to P. So earlier in the chapter, in chapter 6.2, if I want the mean of my binomial, I can take n times the mean of my Bernoulli, because I have n Bernoullis. So in other words, n times p. So the mean of a binomial random variable is just n times p. And then let's real quick talk about standard deviation. So remember my chapter 6.2 formulas on random variables, we can't really use them on the standard deviation, so let me kind of backtrack and use it on my my variance. So remember from 6.2, the variance of my Bernoulli, the variance of my Bernoulli was just P times Q, right? So now I have n Bernoullis. So the variance of n Bernoullis is n times P times Q, right? But I don't really care about my variance so much. I care about my standard deviation. So then I just take the square root of n times P times Q. So that gives us this formula here. This is my formula for the standard deviation of a binomial distribution. Remember, Q was really this probability of failure, which is just 1 minus P. So now we can kind of use those formulas to find mean and standard deviation. So just to kind of formalize this, if the count of x successes has a binomial distribution with a number of trials n and a probability of success p, the mean or expected value is just n times p. The standard deviation is square root of np 1 minus p. Just to remind you, you can only use these if you have a binomial distribution. So think about this kind of situation, bottled water versus tap water. Can people really tell the difference? To test this, a teacher prepares stations with cups of water labeled A, B, and C. 2 of the cups contain tap water, 1 contains bottled water. You drink each and write down the letter of the cup that you think held the bottled water. So you have this AP Stat class. Assume that each of the 21 students in the class who did this, activity was just guessing. So if they just guess, there's a 1/3 chance of each student correctly identifying the cup with the bottled water. So x is our random variable. Let's define x to be the number of students who make a correct identification. This is the histogram of the probability distribution of x, but what is the probability distribution of x? So a trial consists of a student in the class trying to guess which of 3 cups contain the bottled water. They either guess it correctly or incorrectly. Independence, because one student guesses is independent from another's. We have 21 students, and the probability of success, if they're all guessing, is 1/3. So x, where x is the number, we already defined x up here, the number of students who make a correct identification. X is binomial with n 21, and probability of success 1/3. So part B, describe the shape of this probability distribution. We can pretty clearly see it looks pretty much symmetric with a single peak around x equals 7 right there, right? Now let's talk about the mean. We're going to use that formula we just came up with because we established that this is binomial. The mean of the distribution is equal to n times p. N was 21. Probability of success is 1/3, which is 7. So think about it. If all the students, the interpretation, if all the students in Mr. Hogwarts' class were just guessing, and if this activity were repeated many times, that's the important here. Remember, the mean of a random variable is what if this happens over and over and over? That's the interpretation. Then the average number of students who guessed correctly would be about 7. So remember, this probability distribution is if I kind of repeat this if I have like lots and lots and lots of classes with 21 kids, sometimes 10 kids would guess correctly, sometimes even 13, but most of the time about 7 students would guess correctly. And that kind of makes sense. If there's a 1/3 chance of getting it right, 1/3 of the kids should guess correctly. Well, 1/3 of 21 is 7. Standard deviation. So we're going to calculate and interpret the standard deviation in this situation. Again, using our formula, we can just plug in square root of 21 times 1/3 times 2/3 is 2.16. So again, if all the students in Mr. Hogwart's class were just guessing, and we repeat this activity many times, the number of students who guess correctly would typically vary by about approximately 2.16 from the average, or from the mean of 7. So almost all real-world sampling, such as taking an SRS from a population of interest, is done without replacement. This means that with each successive observation, the probability of success, P, may change. Because I'm not replacing. Think about that card example that we talked about earlier. If I take out a card from a deck of cards, it changes the probability of success for the next card, right? But sampling without replacement leads to a violation of the independence condition. But here's the thing. Most of the time when we sample without replacement, we're sampling from a really, really, really big population. Not just a deck of 52 cards. We're sampling from thousands, or a lot of times millions of people, or whatever the case may be. So in other words, if my sample size N is small, in comparison to the population size, we'll use capital N to be population size, then the probability of success always changes, but it changes so very slightly. So in this case, we'll say that the count of successes in an SRS of size N has an approximately binomial distribution. So in other words, we're kind of being a little lenient with our rule of independence. We don't totally have independence, but if that population size is really, really big compared to the sample size, we're just being kind of lenient. This is what we call the 10% condition. So when taking a random sample of size N from a population of capital N, we can use a binomial distribution to model the count of successes as long as sample size is less than 10% of the population size. That's our 10% condition. For more information, I strongly encourage you to read page 446 to 447 in your book. So let's look at a quick example here. So in a survey of 500 U.S. teenagers aged 14 to 18, subjects were asked a variety of questions about personal finance. One question asked whether teens had a debit card. Suppose that exactly 12% of teens aged 14 to 18 have debit cards. Let X be the number of teens in a random sample of size 500 who have a debit card. Part A. Explain why X can be modeled by a binomial distribution, even though the sample was selected without replacement. So first thing, we should really say, is this binomial? Do we have either a success or failure? Yeah, they either have a debit card or they don't. Do we have independence? Well, that's going to be the 10% rule in just a second, but we're going to assume that whether or not someone has a debit card is independent from each other. Do we have a fixed number of N? We took a random sample of 500, and the probability of success, we know that 12% of teens have debit cards. So can we use the binomial distribution? Because we didn't really get independence. If I take, in other words, if I take one teen out of the population, theoretically that changes the probability that the next teen is going to have a debit card or not. But because our U.S. population of teenagers is so big, we're going to say that 500 is less than 10% of all U.S. teenagers. So therefore, we're going to kind of like fudge that independence rule. This is our 10% rule. So that's why we can use the binomial distribution, even though we select our sample without replacement. So part B, use the binomial distribution to estimate the probability that 50 or fewer teens in the sample have debit cards. So that's the probability that x is less than or equal to 50 is equal to binomial CDF. Again, notice how these things are labeled really nicely, right? 500 is the number of trials, 0.12 is the probability of success, and we're looking for our x value of 50. So 9.32. So there's a 9.32% chance, there's a 9.32% chance that 50 or fewer teams in the sample have debit cards. All right, that's it. That's all I have for you guys today. Thank you so much for watching, and we will talk more about binomial distributions in class. Have a great day.